So thank you. Welcome everybody to our webinar, to our monthly webinar as part of our Columbia University Northern Plains Superfund Research Program. I am Ana Navas. I am the I have the privilege to serve as the director for the center. And this is a new center, one new Superfund Research Program center. And our mission is to integrate system science, technology, and traditional indigenous knowledge with the goal to protect the Northern Plains water resources and communities from hazardous exposures with a focus on metals, but we are broadly interested in multiple contaminants that are relevant for the communities. And for our first webinar, we are very privileged to count with the participation of Dr. Paul Bradley, Kelly Smalling, and Marcia O'Leary, and they are going to be presenting their work on the drinking water exposome in the Northern Plains nations. And Paul is a research ecologist and hydrologist with the U.S. Geological Survey, and he's located in South Carolina right now. Kelly is a research hydrologist also with USGS, and she's located in New Jersey. And Marcia O'Leary, she's the director of the Missouri Breaks Research Industries, which is the key local organization partnering with many of us, including USGS and also the Columbia Superfund, Northern Plains Superfund Research Program. And she's located in Eagle Butte, South Dakota. So thank you so much, the three of you, and we are looking forward to your presentation. And thank you, everybody. Welcome. Thank you for joining. So Paul, yes, you are welcome to share your slides and to start whenever you are ready.
All right. Let's get back to the top. See the slides okay?
Yes, great.
Okay, thank you. Thanks, Ana. So give you a quick overview of some of the point of use drinking water research, exposome research that we've been doing in USGS. This is work conducted under the Ecosystems Mission Area, specifically the Environmental Health Program. And the work that we're presenting here is conducted by the EHP's infrastructure or water infrastructure integrated science team that Kelly Smalling and I lead. So the focus of that integrated science team is shown in this schematic. Just as a sidebar here, you'll find QR codes on a number of these slides. You can scan them with your phone and they will take you to additional information. In some cases, they'll take you directly to the publication so you don't have to jot down DOI links, for example. So for the water infrastructure project, the focus is summarized here. It's basically a focus on the human impacted water cycle. For convenience, we kind of broadly categorized it into two focus areas. One is kind of the human wastewater impacts and stormwater impacts on ecological receptors in the environment. On the other side of that is impacts on humans, and the focus there is primarily through drinking water. So it doesn't matter whether you're focused on the wastewater side or the drinking water side, the fundamental challenge in terms of anthropogenic organic contaminants remains the same, whether you're using the TSCA inventories, 85 estimated thousand chemicals, or the Long et al. Estimate of approximately 350,000 chemicals, or the CAS registry, which contains millions of organic substances. The number of organic contaminants that are in commercial production globally and potentially in drinking water resources is very large compared to the number of compounds that are actually addressed in regulatory space. So for example, the Safe Drinking Water Act's National Primary Drinking Water Regulations addresses, depending on how you count them up, roughly 90 compounds. And this theoretical complexity, our field research is consistent results are consistent with this theoretical complexity. This is a collaborative study conducted by the USGS and EPA back in 2012 to 14. This was a national pilot study. It leveraged the analytical capabilities of both agencies together, and amongst other things, analyzed more than 700 target organic analytes. Of these 700 organics, more than half were detected at least once, and of the ones that were detected, more than half of them were pesticides and pharmaceuticals, which are compounds that are designed to be biologically active. And we know that this environmental complexity is making its way through our drinking water treatment facilities in some respects. So this is another collaborative study by the USGS and the EPA looking at 25 drinking water treatment plants and assessing organics and inorganics in the raw intake water and comparing that with what they see in the pre-distribution treated drinking water. And these compounds are making their way through the drinking water processes, and in some cases, essentially unchanged. So based on that, based on input from public health researchers and public health agencies and decision makers, we initiated a drinking water exposure research project in the infrastructure project. And the idea is to support agencies and decision makers by giving them a better understanding of what human exposures in drinking water actually are. And there are two specific design criteria involved in this research portfolio. One is that we conduct the assessments of exposure at the point of exposure. So we're doing most of this work in workplaces and in people's homes, and we're taking the sample directly from, in most cases, their kitchen tap. The other design criteria is that we're going to use a much broader analytical toolbox to represent more realistically the kind of environmental contaminant complexity that we see. So just as a quick overview, there are 3 general distribution pipelines for drinking water in the US and globally. In the US, public supply and commercial bottled water are regulated by EPA and FDA respectively, and then there's private supply. So EPA and FDA regulate. They are both focused on regulated contaminants primarily, and their monitoring and assessment is generally done pre-distribution. There are fundamental differences in the way EPA regulates drinking water, tap water, and the way FDA regulates bottled water. And then we get to private supply. EPA is not authorized to monitor or regulate that. And private supply is defined as less than 25 people and less than 15 hookups. So since the onus and the cost falls on the homeowner, there's very little in general data available on private well exposures. So we've done a number of these tap water, drinking water exposome studies since the initial pilot study conducted in 2016. This talk is going to focus on the 2019 collaboration in the Northern Plains nations. So in 2018, we started interacting with Anna. She started to read us into the ongoing Strong Heart study. And one of the many focuses of that study were the widespread exposure of tribal nations in Arizona, Oklahoma, North Dakota, and South Dakota to arsenic in drinking water and the potential adverse effects on health outcomes. And then that evolved to efforts in the Northern Plains Nation for arsenic interventions. They kind of twofold interventions taking place there. The communities are building and small community water supplies and developing distribution systems for connections to those water supplies to control exposures to drinking water contaminants. And then another ancillary component of the Strong Heart study was the ancillary Strong Heart water study, which was specifically focused on more remote locations in the Northern Plains nations that are dependent on private wells, and making efforts to mitigate arsenic exposures by installing point of use treatment devices, specifically under sink sorptive media devices. So there's good complementarity to our research focus. So we basically scoped out a collaborative effort. So we're going to employ our drinking water exposome approach and apply it to samples collected in the Strong Heart water area, specifically to provide a broader understanding of what contaminant exposures, help identify any other contaminants besides arsenic that are of potential concern for health, and potential gaps or opportunities in existing drinking water systems. So we started those discussions, as I said, in late 2018. We actually started scoping these studies in late spring and summer of 2019. And then there was the open question of whether to go ahead and try and get a pilot scale effort underway in 2019 or to wait for 2020. So we scoped out a pilot scale effort. The idea was to make it, for logistical convenience, to make it a convenient sampling of tap water locus within the Strong Heart water study area. And the intent of this pilot scale wasn't to be the endpoint. It was to be a foundation for follow-up studies, which were focused either on spatial or temporal variability or specifically targeted hotspots like mining impacts. So the analytical toolbox that we're employing in this study and across all of our studies is shown here. It involves collection. Each sample involves collection of about 30 bottles, takes us about 30 minutes. We analyze roughly 500 organic analytes. They include cyanotoxins associated with harmful algal blooms, disinfection byproducts typically associated with public supply, PFAS compounds. It's in the news all the time now. And pesticides and pharmaceuticals, as I said, they are designed to be biologically active. And then the VOC compounds include many of the legacy regulated organics. They have the inorganic chemicals, including trace elements like arsenic and microbial indicator groups, as well as incorporating some bioassays into our studies. We have a number of quality control, quality assurance procedures that we use across all of our projects. One of the most important is that we try to maintain the same USGS sampling team to eliminate sampler variability as part of the equation. Quality assurance includes field blanks and a wide range of laboratory QA samples. Each of these samples collected on ice, packed, shipped daily on ice for overnight delivery to the labs. So we started this initial reconnaissance effort in September 2019. We completed it in November 2019. A total of 56 total tap water samples were collected. 34 of those were from private well locations. 22 of them were from public supply locations. So the first effort was in September in Community B, half samples from private wells, half from the community water supply. The next sample collection in October was Community C, 12 samples from public supply and 8 from private wells. And then the last sample collection was conducted in November, and that was in Community A. And the permit for sample collection for that was just for private well locations that were already part of the Strong Heart water study. So this is a summary slide of the results for the inorganics. We'll break these down and look at them one at a time, but using this slide, I want to orient you on the layout. The communities are arranged on the x-axis, community A, B, and C. The data sets, the blue colored data sets are public supply locations in community B and C. The white boxes indicate private well locations in all 3 communities. On the y-axis is the contaminant concentration in micrograms per liter. This is in a log scale. And if there is a EPA enforceable standard for the contaminant, like an MCL or a technology treatment action level, it's shown as a red bar on the plot. So the summaries are 34 inorganic analytes were assessed, 30 of them were detected at least once in the study. There were no public supply locations where an MCL or an AL was exceeded. There were actually private well locations, however, where the equivalent MCL concentration was exceeded. And then in both public and private supply locations, we had a number of exceedances of health advisories. So walking through these one at a time, for arsenic, obviously the focus of the Strong Heart Water Study was on arsenic. So these results ended up bearing out and complementing those existing data sets. The MCL for arsenic is 10 micrograms per liter, 14 locations. They're all private well locations, actually exceeded this value. So that's roughly 25%. And if you break that down to private well locations, that's about 42% of the private well locations in this study exceeded that MCL. There's growing concern about adverse effects, though, at lower than MCL concentrations. Some states have instituted lower MCLs. New Jersey and New Hampshire, for example, have an MCL of 5 micrograms per liter, and roughly 56% of the private well locations in this study exceed that value. And in Community C, 11 of the public supply locations would actually exceed that 5 microgram per liter value. But arsenic, as is the case for a number of other inorganics, doesn't have a known safe level of exposure for vulnerable populations. The maximum contaminant level goal is 0, and across all study locations, about 54% of the sites had detectable arsenic. So for uranium, the MCL is 30 micrograms per liter. Only one location in this study actually exceeded that. That's a private well location in Community C. The health advisory for arsenic, as was the case for uranium, as was the case for arsenic, is an MCLG of 0, and about 43% of the samples collected across all communities had detectable levels of uranium. So lead doesn't have an MCL. It has a technology treatment action level for public supply. That level is 15 micrograms per liter. There were no exceedances of that value in either public or private supply locations. Lead also has an MCLG of 0, and lead was detected in about 20% of samples in this study. There's no difference in the frequency detection between the private and the public supply locations, and there was no systematic pattern of detection, for example, in public supply locations. So these results are most readily aligned with premise plumbing source of lead. And one note that's important here is that we're not following the EPA's stagnant sampling protocols. So prior use of the drinking water before we got to a given site was common. And so these lead results should be interpreted as potentially significant underestimates. Nitrate nitrogen, MCL is 10 milligrams per liter. The MCLG is the same. The focus here is on methemoglobinemia. There was one private well location in Community B that exceeded that value. There are growing concerns of adverse health effects like cancer after prolonged exposure to drinking water nitrate concentrations less than the MCL. Manganese results, there's no MCL for manganese. The EPA, however, does publish some public health advisories. One is a drinking water health advisory, 300 micrograms per liter. This is a lifetime metric, and it assumes 100% drinking water exposure. The impetus behind that is neurological impacts in children. And we had roughly 32% of the samples collected in this study exceeded that value of 300. And that includes public supply and private well locations, most notably in Community C. One notable result here is that the EPA also promulgates a one-day acute exposure value of 1 milligram per liter for small children, defined as less than 10 kilograms. And we had a location in Community C, a private well location, where this value was exceeded. And this is in the same sample that had the higher than MCL uranium concentration. So that's obviously a significant concern. The World Health Organization has also published a provisional guidance value of 80 micrograms per liter, again, focused on neurological effects in infants, in this case, primarily focused on bottle-fed infant exposures. And the number of samples that exceeded that 80 microgram per liter is about 39%. Then selenium. So the MCL for selenium is 50 micrograms per liter. There were no exceedances of that value. MCLG is the same. The European Commission has a parametric value of 20 micrograms per liter for selenium. There's one site in this study, a private well site in Community A, that exceeded that. And then there's a series of publications from a cohort study in Italy, which has suggested a drinking water maximum of 1 microgram per liter. And if you want to apply that recommendation, about 16% of the samples across this study exceeded that. And in Community A, more than half of these private well locations have higher concentrations than 1 microgram per liter. So moving on to the organics, this is a map display of the results. Increasing darkness of the color indicates an increasing cumulative concentration of all organics detected in a sample. The symbols indicate private well locations, that's the circles, and then diamonds are public supply locations. And then the size of the symbol indicates the relative number of detection of organic compounds in a given sample. So of the 476 organic target analytes assessed in this study, 63 were detected at least once. They're shown here from top to bottom in the order of decreasing frequency of detection. There were no exceedances of any MCLs in public supply. Several of these detected compounds, however, have MCLGs of zeros, and those were exceeded most frequently in public supply, disinfection byproducts, bromodichloromethane, bromoform, or tribromomethane. If you prefer, dichloromethane frequently detected together in multiple samples in public supply, and then single detections in private well locations of 4 other VOCs. So these are the organic results, which are aggregated and broken out by classes. So the upper left-hand plot here, each of these circles represents the cumulative concentration of all organics detected in a sample. The boxes are median and interquartile ranges. And then for these plots, again, as before, the blue field indicates public supply locations, the white field is private well locations. So if we look at the organics and then move across to disinfection byproducts, we can see that in public supply, most of the detected concentration is associated with disinfection byproducts. Just for a frame of reference here, EPA has an MCL of 80 micrograms per liter for trihalomethane, and the cumulative concentration of disinfection byproducts in both of these community water supplies is well below that regulatory standard. Other compounds that were detected in public supply are some VOCs, xylenes, and terpbutyl alcohol, generally at less than 1 microgram per liter concentrations. And then in Community B, 7 of the public supply samples are associated with a surface water source, specifically the Missouri River. Missouri River is obviously passing through agricultural landscapes. It's picked up pesticides, and so we've detected pesticide concentrations in those 7 public supply samples in Community B. And you look over to the private well samples here. So the white boxes here in the upper left-hand corner, those are all primarily associated with VOCs, so kind of intermittent detections of VOCs. The highest detection, cumulative concentration of detected organics in this study was a private well location here in Community A. This is driven primarily by a single compound, isopropyl alcohol. There are a couple of other locations in private well locations across the study area where we detected mixtures of petroleum hydrocarbons, and that indicates that some sort of fuel transfer process on these remote locations, and it's managed to work its way into the shallow drinking water aquifer. So obviously the intent here, so risk is some function of exposure and hazard. So we've documented the exposure, and to get some sort of insight into risk space, we've used a couple of kind of hazard quotient approaches to assess relative risk, and specifically focusing on the cumulative risk in the mixture. So the first method we use exposure activity ratios. This is a ratio of the measured concentration divided by the activity concentration at cutoff from the ToxCast database. There are some advantages to the ToxCast database. It now has coverage of more than 10,000 organic compounds. It has exposure response data on more than 1,000 primarily molecular, human-centric or vertebrate-centric, if you prefer, molecular endpoints. And the advantage to these kind of hazard quotient approaches is that you can calculate an individual contaminant's exposure activity ratio, and then you can add up all those individual exposure activity ratios for a sample and get some insight, in this case, in the potential for biological effects of the overall mixture exposure. There are some distinct disadvantages to this approach. The obvious intrinsic one is incomplete analytical coverage. So 460 target organic analytes is a very large exposure data set, but it's very small, orders of magnitude underestimate in comparison to the potential contaminants present in the environment. And then there's also this ToxCast, incomplete ToxCast coverage. In this case, of the 63 compounds, organics that were detected, only 32 of them had ToxCast data. In terms of the molecular endpoints potentially give you more insight, more sensitive understanding of potential biological effects, but there is the open question of whether those molecular level effects actually translate up to the organism level. And then the biggest limitation to the exposure activity ratio method is that the ToxCast data set is on organics. So looking at the data, the sites are arranged here along the x-axis for communities A, B, and C. The exposure activity ratio is on the y-axis. This is again in log space. For each of the sites locations where there's no data above it, then the exposure activity ratio was considered insignificant, less than 10 to the minus 5. For those with data, the circles represent the exposure activity ratio of a single compound. And then for that sample, all of those individual compound ratios are added up to give you the red triangle, and that is the cumulative exposure activity ratio. And so we're using, to interrogate these results, we're using two screening levels. The simple, obvious one is an exposure activity ratio of 1. For a single contaminant exposure activity ratio, this means the measured concentration exceeded the demonstrated in vitro effects level. And then we're also using, as a precautionary screening level for concern or follow-up investigation, an exposure activity ratio of 0.001. And this is 3 orders of magnitude lower. We're doing that because the ACC value is a direct activity measurement. It has no margin of safety built into it. And then also because we're pointing back to the fact that 467 analyte space is a orders of magnitude underestimate of potential exposures. So you can see from these results, there are a number of locations that have individual as well as cumulative exposures that are above this 0.001 screening level. The other screening level that we're using is toxicity quotient, or hazard quotient if you prefer, or risk quotients. Same kind of mathematics, measured concentration, in this case divided by a health benchmark. And the advantages to the TQ, and the reason we employ it in addition to the exposure activity ratio, is because it allows you to include the inorganic exposure as well as the organic exposure. The health benchmarks actually directly inform human health effects at the apical level. Most of these benchmarks essentially all the ones we use include a margin of exposure so they can be easily interpreted. Below this margin below this benchmark, there is no known risk of to the health of the most vulnerable subpopulations. As is the case for ear, you can sum up individual TQs to estimate the mixture TQ. The disadvantage, as was the case for exposure activity ratio, is the analytical underestimate that's inherent in this approach. And then in terms of the denominator, you're limited to available benchmarks, which by definition means that there's poor coverage of emerging concerns. So looking at the results again, sites arranged along the x-axis, TQs on the y-axis. The interpretation here, screening-wise, is simpler. TQ values greater than 1 are an elevated risk to human health. TQ values of less than 0.1 are generally interpreted as low or no risk to human health. And so the simple interpretation here, when you include inorganics as well as organics, is that every site in this study is exceeding that 0.1 threshold of no risk, and most of the sites are exceeding the TQ of 1, indicating elevated levels of risk. Again, this is incorporating both inorganic and organic exposures in the assessment. So these results are published now. The QR will take you to the publication. If you have any questions about it, we can answer them today, or you can reach out independently. Before I close here, I want to go ahead and do the kind of due diligence here for these point of use drinking water exposome studies and complete our understanding. So you've seen results here for private well locations, you've seen results for public supply locations. What about for bottled water? So a lot of people are concerned about drinking water exposures to contaminants, and so a lot of people are considering the shifts are already actually shifting to bottled water with the expectation that the bottled water is safer. So we did a study which was just published. You can follow the QR code to the link. We did the same analytical toolbox. We assessed 30 bottled waters that are commercially available in the US. 7 of them are imported. Those are shown on the plot on the right as blue fills. The others are domestic samples. 7 of the locations here are purified tap water. So they're taking tap water and they're subjecting it to some sort of advanced purification method like RO. The others are spring water locations. And so that's a TQ plot on the right. And you can see that the majority of those bottled waters are exceeding that 0.1 threshold for no risk. And many of them are well above the threshold for the same evaluation of the risk threshold. So a direct comparison here, just using 3 examples: nitrate, nitrogen, and arsenic and VOC. And these are data from multiple studies that we've conducted. The private well is the blue on the left, public supplies in the center, and then the bottled water results are shown on the right. And what these results are illustrating, and this should come as no surprise, is that basically no matter what your drinking water distribution pipeline is, they're all being challenged by these contaminant challenges. So to close here, and before I turn it over to Marcia for her comments and input, a number of these studies are being conducted. The Northern Plains collaboration with the Strong Heart Water Study back in 2019. I think Anna will probably jump in and remind me of this. We were going back and forth on whether or not to try and squeeze this in 2019. We went ahead and pulled the trigger and did that. In retrospect, by February of 2020, it was obvious that was a really good idea because we got shut down for field work for a couple of years with COVID. So if we had waited, we wouldn't have these results. And the intent here is that these Northern Plain results are, as I said before, a foundation for continued study, including collaboration with the CUNP SRP. Some of these tabular results are being aggregated into a storyboard or a geo-narrative, if you will. You can follow the QR to that. The intent here is to have one-stop shopping on these studies, and they'll be added to it as they're published and released. And now I'll turn it over to Marcia for her input.
Well, first of all, thank you, Paul and Anna, both for bringing this to our communities. Obviously, one of the key things here is that without some of this baseline information, much of this wouldn't have been known, because there's very few entities that have the funding to do the kind of analysis that you were able to provide our communities. So you can't change what you don't know, right? So I'll speak more to the role and the processes for partnering with our tribal nations, and how key that is in order to bring this data to our communities. You know, first of all, each of our tribal nations are unique; they're all different. So the processes in one doesn't necessarily translate to the next tribal nation. So for us, tribal approvals is a process. Some communities are very, very sensitive and have a lot of political wherewithal around the issues of water. Others are, very much open to it. And there's just lots of factors around it, lots of history. And we know that a lot of the history that has brought our tribal nations to this, has been a hard row. So there's been a lot of mistrust. And so we have to be very respectful and very open to the processes that they have established. And so we were really lucky. Lucky is maybe not the word, but we were really appreciative when we were able to move forward as quickly as we were able to. We went to each of our tribal nations and got approvals. And I think one of the big issues that made this possible was the listening, because each of them wanted something else out of this. For one nation, they were very, very concerned and had lots of pushback about public water sources. Another one didn't want any public water sources tested whatsoever. And others, each of them had their own outcomes already in mind. So that was important for us, and we had to be very respectful and make sure that we were listening to and responding to what they wanted and what they needed. And of course, one of the big issues in anything that we do, and it needs to be key in anytime research is done in our tribal nations, is that it involves capacity development, whether it's bringing on students. And I know that we've partnered with Anna on a couple of different projects that are going to be, and the Superfund project, and as well as Ben on, and with Esther, I see her on the call as well, and Joe Hoover, working towards trying to develop capacity in our youth, in our the feedback that we're giving back to our communities. Those are all critically important, because the day of just coming and taking and getting information and then having it, and I hate to, this is kind of a silly thing to say, but the drip down theory process doesn't work, even with water. So we have to go ahead and actively return data. And we also have to recognize that as sovereign nations, our tribal nations own the data, and we have to respect that we are using their data to further everybody's good. But in the end of the day, they own the data, and we must ask permission to use it. So you can go to the next one. We know that, to misquote Martin Luther King, we know that clean air, clean water, and clean environment are a basic human right. And so for our communities, it's because we are living in environments that are just on the cusp of drought at any time. Water is just critical. And of course, many of you are familiar with the Standing Rock event that happened here a couple years ago, where they had, they tried to stop the pipeline from coming through. And the unfortunate issue is that we don't have a lot of baseline information. So the information that Paul and Anna are bringing with the USGS survey really did bring some baseline information. And so those are all really critical information for our nations to have, and it'd be hoped that it would continue. So, and finally, the last slide that I'm going to present is just because I think children are our future, right? And I think that clean water is just a key to all of what we do and how we do it. And so I would leave you with this wonderful picture of children. And I'm happy to answer any questions that you might have.
Wonderful. Thank you. Thank you so much, both of you, for your wonderful work and presentation. And let's open it up for questions. So maybe, Paul, if you want to stop, you can, and we can see if people want to put their cameras on, and we can start like a dialogue and questions. So I don't know if there is somebody who would like to ask a first question. Anybody?
So we've answered all the questions. That's wonderful.
I think people are happy with the presentation. I think we've learned a lot. It's impressive. I think I will start with just one specific question that I thought was very interesting, is because I had forgotten, is about the manganese finding. And there seems to be such a range in the levels for manganese. And so I wanted to ask, is that because I don't think we know enough, honestly, about water and manganese in water and health effects. So that's, is that something, should we be studying that more? What type of work we can do? I know that, I don't know if we can, where is it come from? Is that a pure geological thing happening? Is there something else? So I don't know, Paul, if you can help us with some of these manganese findings.
Yeah, I mean, I can comment on it. You also have geochemical experts on it. They can all chime in on it. One of the challenges to private wells is, the impetus for putting that private well in is to get water, right? And so they go as deep as they can to get a reliable water supply. But by and large, it costs, not just in tribal nations, but it costs the homeowner across the nation. And so the depth of those wells is often limited by available resources. So in a shallow private well, in order to ensure water supply, they're generally as large an open hole area as possible, right? So they're taking water across a very large depth range to ensure that they always have water supply. Well, and that works as a strategy for water supply. Unfortunately, one of the trade-offs there is that it pretty much guarantees that you're going to run across different redox zones. And so that's redox variation in terms of space and depth, but you also have redox variation in terms of time. So as the water levels change, as the infiltration from the surface changes, you get changes in redox zones. And so one driver of that is microbial activity. Microorganisms will sit there and they will breathe alternatives to oxygen. So they start preferentially with oxygen, then they'll move down that redox suite, that terminal electron accepting process suite. One of the first ones they run into is nitrate. Right there in that same neighborhood is manganese and iron. And so they will start to breathe manganese and iron, and that will tend to release those into the dissolved phase. And then as they move past that, then they start to get down into sulfate reduction. You get your sulfide odors produced, and then they get to, for example, CO2 reduction, and that's methanogenesis. So if you're running across those redox zones, you know, there's a good chance you're going to see those species. And if the conditions turn reducing, you're going to see those species. One of the challenges to it is that arsenic is mobilized under reducing conditions. Jump in, folks, if you need to. And uranium is mobilized under oxidizing conditions, right? So normally you would not expect to see those both showing up in a well, but if your well is sampling heterogeneous conditions, then you're going to start to see that. And we see that in these samples where you have arsenic exposure and uranium exposures occurring in the same well.
Mm-hmm. Wonderful. Thank you for this clarification. Any other questions? I have another,
one of the questions that I have, Anna, is that, we know we're learning a lot about mining impacts, but how is that? There's a move in this country now towards hydroelectricity, right? And also, we're seeing more and more cattle confinement happening in our part of the world. And how is that going to impact, because I would think fracking in terms of the hydro energy development, but with these very, very deep wells, and would be something that we're going to have to be on the lookout for, but equally so would be our cattle confinement and the risk for polluting our large bodies of water, such as the Missouri River. And what can we do as to ensure clean water for our future and to prevent mishaps?
Well, that's a really broad, open question, and I know there are definitely a lot of opinions on that in the call space here. I think to step back and make the response very general, and hopefully it was the message that was presented in this seminar, is it's a shared problem. We are impacting our water cycle. We have to pay attention to the potential activities or potential impacts of any of our activities on our drinking water supply. And so, concerns about, for example, in the Northern Plains nations about mining effects and potential on drink, those are legitimate. And so you need to understand the hydrologic system to understand if that's a real concern or not. In terms of your question about CAFO operations, we just published another study. Maybe Kelly, you can drop a link to that one into the chat. And that study was conducted so obviously the Northern Plains study includes agricultural landscape, but at least where we were collecting samples, there weren't many CAFO operations. There wasn't a lot of, quote, intensive agricultural. We just completed a study in Northeast Iowa, which I think anybody would describe as agriculturally intensive. And the signals that you're seeing over there are lengthy mixture of pesticides. Those are coming from that surface. So they're infiltrating from those surface applications down into the ground. And, you see the pesticides from crop ag. You also see indications of manure waste working its way down into their drinking water supply. And again, the same perspective about private well locations, the cost benefit analysis on how much money you have and how deep you can afford to go. And so you generally have these shallow open hole wells that are close to the land surface, and their drinking water supply is going to be affected by that agriculture. And so if we didn't have, and you'll see in that study, there's a map there that specifically identifies all the CAFOs that are in the area in Northeast Iowa, and it's a lot. So yeah, those will have an effect on shallow systems. And I think the broad answer is we have to be aware that what we do impacts our drinking water, period. And we have to take steps to try to protect it. And I think we also at this point have to consider, in many of our locations, the impacts are there. So we have to take steps to improve the treatment, which may include, doing point of use treatments to augment any kind of a treatment that may be provided by your drinking water supplier. If you're in a private well location, you really need to start thinking about that, because, you can't afford to do a monitoring effort. I'm a private well person. I can't afford these analyses, which means that effectively I have no clue what I'm drinking, right? So then we have to make decisions about how we treat that water.
I have a question, Paul, because something interesting to me is when you look both at the private wells and the public water, if it were not because of the inorganics, the private well water looks so much clean in general.
Mm-hmm.
It seems that there is less stuff in it, except for the inorganics, the very toxic elements that we don't want. So is that something that we could leverage in a way, like in a place like, in the Northern Plains, where they have really great groundwater resources? Is that something that could be leveraged better in a way for the community water systems, if we were able to treat and remove the inorganics in a simple way, which I know is not simple?
Yeah, the inorganics exposure is a mixture. So you have to come up with treatment options, that are not just, for example, going to address arsenic, but are going to address arsenic, selenium, manganese, uranium, things like that. Yeah, and the pattern is very real, and there are real questions that need to be asked in public supply space. There are real questions that need to be asked in private supply space. So in public supply question is this trade-off between what we know is an acute threat to human populations, which is pathogenic contamination. So you need to prevent pathogens in your drinking water supply, so you disinfect. And it's very important to understand that disinfection works very well for reducing the mortality of pathogenic contaminants. The trade-off is that it generates disinfection byproducts, and there is a growing appreciation that there's a cost associated with those. And so that means, in my mind, that we need to make efforts to improve how we disinfect things, right? It does not mean we stop disinfecting things because we don't want to go back 100 years and have those high mortality incidences. And in terms of the private well locations, if you have this kind of data, so if we work together and we get this kind of data, then you can start to make decisions like that. I'm on a private well. I know I'm exposed to arsenic and uranium. I can treat them here at the point of use and stay on my private well versus, getting onto the community water supply, and then I need to make decisions about disinfection byproducts. What I hope the message was from this presentation is that all three distribution pipelines have their challenges, and to address those challenges, well, there is no option for ignoring the fact that they have challenge. You can ignore it, but that's not reality, right? So to address the challenge, you need the information so you can make decisions about relative risk and what you're comfortable with.
So Paul, I just have to circle back around on my question on hydrological energy production. As the world's quest for energy is more and more, and it seems to never end. There seems to be a growing interest in artesian wells as a source of energy for energy development. And I'm just wondering, it's similar to fracking, but they say it's not. Do you think that's something that we need to be thinking about and concerned about in our rural areas in terms of using the artesian wells as a source of energy? Because again, you're polluting deep holes, right?
Yeah, I don't know enough about those concerns. We have other research projects that are specifically focused on things like fracking impacts on drinking water supplies. So I don't know enough to speak directly to that. Steve, I see your hands up. Do you have a comment on that?
Oh, Steve, we cannot hear you. You need to unmute.
Sorry, no, not on that, but on the earlier discussion of point of use. You were stressing point of use for private wells, which I totally understand. But your data suggests that some people, if they wanted to avoid risk, might think of a point of use even for public water supply, which is that risk you have to compare to other risks and the costs are not necessarily small for a point of use system. But I'd be interested in your take on the risk in public water supplies. I used to say they were safer than private wells and safer than bottled water because they're tested. But you nicely pointed out that they're only tested for a few things, and that they tend to always have some disinfectant byproducts. But they also, we've seen in the last decade that they have a lot of PFAS in many public water supplies because it wasn't being tested. And so, that sense of security from the testing wasn't really there. What's your thought on point of use for people or point of entry for people on public water supplies? I'd be interested.
Yeah, I'm all about getting the information to the end user so they can make the actual determination about their own, comfort level. And that means in private supply, well, unfortunately, the bar is really low. Pretty much any information is new information for private supply. In public supply, I would say, so the regulation under EPA, they have to put out community right to know information. So they have to publish it. You can find lots of information on what's in your public supply water, and that's a big win. That's a big plus. Yes, there are limits to it. It focused on regulatory space. There's another inherent limit to it is most of the information that you get will be relative to the MCL. And there will not be as much information about concentrations below the MCL. And we as researchers and public health researchers specifically, we have lots of interest in what the human health impacts of below MCL concentration. So I'd like to see public supply information, be a little more transparent at the lower concentrations down to their detection limits so that people can make decisions. And yes, I would say that I think in a lot of locations, if you're on public supply, consideration of point of use treatment is reasonable. There are locations like, and Maria Argos is on, she can speak to this. We did a study in Chicago prior to 1986 and the Safe Drinking Water Act amendments. In Chicago, you were required to use lead in the distribution system, which means that Chicago's public supply has lead in it, period. So they have a very good source water. It's Lake Michigan. They've been protecting that source water for more than a century, right? But then they have this other thing that pops up in their distribution system. So what would be the response? Well, if you could afford it, I would suggest that you treat at your tap to take that down, especially if you are pregnant or have young children. So I do believe that, well, the other reality that we live in is we're water short. To meet our water supply needs, we're having to reuse water. This issue of human impacted water is only going to increase. There are fundamental cost limitations and technological limitations on what a drinking water treatment plant can achieve per dollar, right? So you either increase your support of that drinking water treatment plant or you augment your treatment at your own tap. And as a private well owner, I augment my treatment. I treat at my tap.
Thank you. Thank you so much, Paul. And we are now at the limit at 4 p.m. my time. And I know it's 2 p.m. in other places and other times in many different places. So thank you, everybody, for joining. I think this was an incredible conversation showing that we need to continue doing this work. This is a foundation, as Paul and Marcia highlighted earlier. And this information is very important for action. I also want to thank Nancy Kyle, because you had this very important comment related to this mine in Nebraska that might be very relevant for us, for our communities. So thank you, everybody, and we'll continue meeting regularly every month to discuss these types of issues. So thank you again, everybody, for joining today. And bye-bye. Thank you.
Thank you. Take care.
Thank you.